So now that we've just finished talking about sequences, we're going to progress one little step and talk about series. You see, with sequences, we did stuff like this. We said, suppose we have a sequence of terms, and it goes for a while, and we looked basically at whether this sequence would converge or whether this sequence would diverge. And I showed you in the last section basically how to do that. Remember, we're taking the limit of it, working with the limit, maybe using the squeeze theorem, sometimes doing the comparison tests with that. Well, now we're progressing a little bit further. If we have a sequence and we say, well, now I want to do something more than just look at the terms as being a list. What if I wanted to actually add them together? As soon as we take that sequence, we go, no, I don't want to just list them out. I want to add them. What we get is called a series. Now, there's a couple different ways that we're going to look at series. The first notation that I'm going to introduce to you, and you've seen this before, it's probably been a really long time since you have seen it.
Sigma.
Yeah, it's with that sigma notation. So when we use this capital Greek letter sigma, sigma S stands for a sum. So whenever we see that, we have a sum. So what we say here is, okay, suppose that we have, remember that notation? What would that stand for?
A sub n.
That would stand for, if I did this, would be a sequence, no? Now it says, okay, cool. So I want you to take these terms of your sequence, and I want you to add them together from where I tell you to start to where I tell you to end. That right there would be a series. Are you guys okay with the notation of a series? Quick head nod if you are okay with that. So here's what this would do. This would say, okay, here's terms of your sequence, right? Boom, 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 boom. So boom, boom, boom. This says you add them together instead of just list them out. It tells you where to start, and it tells you where to stop. Where do we start?
N equals 1.
1. Where do we stop? We
We
do not stop. We keep on adding them and adding them and adding them and adding them. Now, there is another way that we're going to consider this. We can look, oftentimes, as where we're going to work with a lot today for the next probably 30 minutes or so, we can work with what's called a partial sum. Can look at what's called a partial sum. I want you to consider the comparison of these two things. Firstly, would this still be a series?
Yes.
Where would it start?
1.
It would start at the first term when I plug in 1 for k. Notice how I'm using a different index here. I'm not using n, I'm using k. Because where does this series stop?
N.
That's right. So here's what this would do. If I say, no, I don't want to start at 1 and go to infinity. I want to start at 1 and go to 100 or 1,000,000 or something finite. Well, this would add up all those terms. Now, here's the point I'm trying to make here. Do you understand that n is going to be your stopping point? So because n is finite here, then what we're going to get is something that for sure exists. Because this is a finite number of terms, because we start at 1, we're going to add these things up. We're going to go, hey, what's the first term? Cool. What's the second term? Cool. What's the third term? Cool. What's the nth term? Cool. Add them all up. Is that for sure going to be there? Yeah, if I say, hey, here's some series and add up the first 10 terms, you can do it, can't you? First 100 terms, you can do it, can't you? The first n terms, you can do it, can't you? The first infinity terms, I don't know. I don't know what that might be, because that goes forever, right? But as soon as I say, you know what, n's a finite number here. So because n is finite, n is finite, that's a finite number of terms. This has to be some sum. So let me go over that here real quick because I'm gonna use this information just a bit. So we have this thing called a series. What a series does, it says, hey, you know what? It's no longer just a sequence. It's no longer just a list of terms. Now we're going to add those terms together. That's what this stands for. Generally speaking, this is what we're trying to do here, folks. We're trying to start at our first term and add up all the terms for infinity. This is what we're trying to do. Now, because I can't just add things forever, because I'm not going to live forever, probably. You never know. But because I'm not going to live forever, I can't add them forever. So what I'm going to do is I'm going to try to work around this idea. I'm going to say, you know what, wait a minute, let's not go forever, let's go to a finite number. Now because I'm starting at the number 1 for my terms here, so the first term, and because I'm stopping after some finite amount, I'm going to be able to add those terms together. Does that make sense to you? This sum has to exist, because n's finite, s sub n, your sum, your partial sum, this is called a partial sum here, your partial sum must exist. Show of hands if you understand that concept. Okay, now here's the important part about this. You understand it's finite, right? This can be a number like 10, or 100, or 200. Do you understand that for every additional n, so if I go from 1 to 10, that's going to be a number, right? If I go from 1 to 11, that's going to be a different number. If I go from 1 to 12, that's going to be a different number. 1 to 100, that's going to be a different number. Do you guys get the idea? Well, then what's going to happen, little subnote here, for, I'll call it the next n. For the next n, so the one right after this one. Remember, these are, by the way, just so you don't lose track of what we're doing here, that n, that still has to be positive. It still starts at 1, and it's still just your integer. It can start at 0 sometimes, but it's just your integers, all right? So it's not like any real number. They are positive integers here. You with me? Just like on sequences. We're basically just taking a sequence and adding up the terms. Okie dokie. So for the next n, that means, hey, stop at 10, now I want you to stop at 11, now I want you to stop at 12. So for the next n, we're going to get a new s sub n. We're going to get a new sum. Here's the interesting thing. I'll try to put it all together for you, all right? Put it all together. Sequence if I don't add them, series if I do add them. This is the way we write series. What we're trying to do is figure out this sum, the sum of this series. Now the way we're going to do it, we're going to look at a partial sum. We're going to say, cool, let's go from 1 to a finite number. Because we're going from 1 to a finite number, this sum has to exist. Now for every next n that I get, I'm going to get a different partial sum. Does that make sense? If I get a different partial sum, then check this out. This is pretty cool. If I just go from 1 to 1, I'm going to have a partial sum. 1 to 2, partial sum. 1 to 3, partial sum. 1 to 4, partial sum. 1 to 5, partial sum. So for every additional n, I get a new s of n. This creates a sequence of partial sums. Do you get that idea? That's kind of cool, right? That's weird. That's why we cover sequences. This creates a sequence of partial sums. Well, let's think about the sequence of partial sums. This is so nice. The notation works for us. If I go from 1 to, if I stop at 1, look at that, n would be 1. N would be 1. I would get s of 1. If I stop at 2, I would get s of 2. If I stop at 3, I would get a sum of the first 3 terms. If I stop at 4, I would get a sum of the first 4 terms, and so on until I get to wherever you tell me to stop. I would get that many different terms. Does that make sense to you? This is our sequence of partial sums. Now here's the main notes for us, and we'll get into some examples in just a minute. This is all like the theory behind it, our base, okay? This is our foundation. So here's some notes for us. Why we did sequences is for the next couple statements that we're going to make. You see, because I'm going to a finite n, yeah, that's got to exist, but because every n would give me a different sum, that creates a sequence for me. The first sum, the second sum, the third sum, the fourth sum, the fifth sum, the nth sum. Well, because that's a sequence, here's a couple things we know. What we know is that if the sequence of s sub n converges, if we know that the sequence of s sub n converges, then the limit of s sub n will have to exist. So this, by definition, our limit of s sub n would equal, let's call it s, as n goes to infinity. Well, then this is what this is going to show for us. I'm going to show you the notation here in just a minute. But if your sequence converges, check this out. This is pretty cool. If your sequence converges, that means that this sequence is going to one specific number, correct? That's what convergence means. In fact, that's what this means, right? It says, hey, look at that. Your sequence as n goes to infinity is giving you a specific number. Does that make sense to you? Your sequence is going to one number. That's what was our definition of convergence here. Well, what are the s's? What is s sub n? It's a sum. It's actually a sum of whatever this thing is, right? Now stick with me here. This is where we make the jump, the calculus jump, because this uses limits, okay? So do you guys understand that our s sub n's, our s sub 1, that's a sum, and s sub 2 is a sum, and s sub 3 is a sum, and s sub n is a sum? Now, check this out. If your sequence converges, the limit of your sequence as n approaches infinity would exist. That means that your s sub n term as n approaches infinity is going to be there. That means your sum as n approaches infinity will exist if your sequence of partial terms is convergent, if that converges. What that means is that if this happens, okay, one more time. S sub n's a sum, right? If this happens, you know what the sum is. That's the idea. Does that make sense to you? Because this says, hey, you know what? Stop at 10. Stop at 12. You're going to get sums, aren't you? Now, don't stop. Well, you got to look at your sequence. If your sequence converges, you go, okay, cool. Go to infinity. Your sequence is there. That sequence converges. That sum exists. That's the sum of your series. That's the idea. You just keep on extending it one term at a time, until you get to infinity. And then if your sequence converges, that means that the limit of your sequence gives you that one number. That one number is your sum. Let me write some of this notation out. We'll go over it one more time. So I'm still getting some glossy looks from you. Kind of glossed you over there. What? Let me show you some notation. I'm guessing it's going to make some more sense, okay? So I'm going to throw a limit up on the board here real quick, show you how this relates back to your limit of your partial sums, and then we'll hopefully get to it. You guys ready? Let's start with this. So we have a sum or a series of a sub n from n equals 1 to infinity. Here's the idea. The idea is, dang, I don't know what that's going to be. So here's what we're going to do. We're going to make this equivalent to a partial sum. But the only way we can do that is to do this. This is an important part, okay? Check it out. So here's the idea. You go, okay, let's consider this, instead of going from 1 to infinity, let's change our index here. Let's go from k equals 1 to n of a sub k. Here's my question to you. Let's see if you have a calculus brain today. All right. Here's my question. Are these equal right now?
No.
Why not?
You need to take a look.
Aha. So n would be a finite number, wouldn't it? Do they start at the same place?
Yes.
Yeah. And these terms would be the same. This would be based on k. This would be based on n. But no big deal. You get the same numbers out of it. All right. However, this one don't stop. This one does stop, doesn't it? So how can I make this expression equal this expression? How can I make this equal?
The limit.
Limit. Where would n go?
Infinity.
Perfect.
Got calculus brains.
You got calculus brains today. That's good. Now do these look the same to you?
Yes.
This says, hey, you're going from 1 to n, but now take n to infinity. That creates this for us. Well, here's the cool thing about this. We already have a definition for what this thing is. This right here is your partial sum. Do you see it? Okay, so stick with me here, folks. Stick with me. Here's the jump. Here's another jump, okay? So Because this is a partial sum, because we're going to, from 1 to a finite number, yeah, we're going to take the n to infinity later, okay? This is what we're doing later. Because we're going from 1 to a finite number, you said this thing has to exist. Remember saying that over here? You said this thing has to exist. All this stuff says that. Well, then this equals S sub n. You guys with me on that one? This part is S sub n. Does that make sense? Now check this out. We've already talked about this. This is a sequence. This is a sequence, S sub 1, S sub 2, S sub 3, all the way to S sub n. In fact, we've talked about this. If this sequence converges, this is going to go to a finite number S. If that sequence doesn't converge, then it doesn't go to a finite number S. It doesn't go to a specific number. It goes to infinity or negative infinity or something alternating like we had negative 1, 1, something that where the limit does not exist. However, if this does exist, that means that, well, let's read it back. If the limit of our sequence S sub n exists, that means that the limit of our partial sums exists. The limit of our partial sums is our series, and that's what we just made it down to. Show of hands feel okay with this statement. So basically it says, all right, got a series, infinity, call it a partial sum. That partial sum, I don't care what it is. This partial sum right here has to exist. Bam, we already said. If I take a limit, this may or may not exist. I don't know yet. I don't know, okay? But if it does exist, it says, here's what's going on. You have a sequence of terms, yes? This is a sequence of terms. Those terms stand for partial sums. They stand for the sum. If I take the sum at infinity, that's what this stands for. This is the sum at infinity. Well, if that converges, it means it goes to a specific number. That would be our sum of our series. You guys with me? I hope I explained it well enough for you to understand. Did I do that for you? Okay, some people get all like, oh my gosh, how is this a sequence? Why is it relating? Well, it's relating because you have a sequence of terms which are your partial sums. Because we can go to infinity with the sequence, we can go to infinity with our partial sums, we can go to infinity now with our series. That's the idea. Would you like to see an example? Example?
Yes.
A simple example. Whatever.
Tongue twister.
It was a tongue twister. Last thing, just so we know this, maybe it's an obvious statement to you. If the sequence S sub n diverges, what's going to happen to our series? It also diverges. Typically, what's going to happen, if this diverges, this goes to infinity or negative infinity. You add up to something that goes to infinity or negative infinity. Sometimes you'll get the just diverges, the limit does not exist, therefore you can't do it. Example time. Do you have any questions on this whatsoever? Because I'm going to erase it, we're not going to talk about it anymore. This is all the theory behind it, we're just going to do examples now. So do you get the idea of a series, that's terms being added together? Yes, no?
Yes.
Do I get that we can find a partial sum no matter what? Because it's finite. When I take a limit of a partial sum, it goes to my series. Therefore, if my sequence of partial sums is convergent, my series is convergent. If the sequence of partial sums is divergent, then my series is divergent. That's basically it. What's also very cool is that when I do my limit, I actually get the sum, which means I've added up that series. Because that sum is going to infinity, because the sequence of partial sums is going to infinity, when I get there, that is my sum of my series.
Cool.
It is cool. I think it's cool. It's very interesting to me.
Saves time too.
I just wanted to make sure you see the interplay between the sequences and the series, because some people are like, well, we did sequences, now series are completely different. Well, we're using sequences in our series here. So example. Por ejemplo. N goes from 1 to infinity of n. Something very simple. Here's the idea of what you're supposed to do. The first thing that we're supposed to do, I wish I could have left this on the board, but this is good enough. The first thing that we're supposed to do is we need to find a partial sum. Because ultimately, here's what we're doing. We're going to try to do this whole thing, right? Typically what we'll show is we'll show this to a partial sum, and if that partial sum, the limit of the partial sum exists, we're good to go. So we gotta find a partial sum. Now that is not as easy as I just made it seem. Sometimes they are very difficult to find. In this case, this one's going to be fairly straightforward, but this is not always the case. So S sub n, that's our notation for a partial sum. Can you tell me what the partial sum would look like?
1 plus 2 plus 3 plus...
Okay, so the partial sum says take this and then start adding up the terms in there. Adding up the terms of a sequence. So the terms of our sequence would be 1, yeah, and then 2, and then 3, and where would I stop?
N.
Very good, I'd stop at n. Should hands feel okay with that so far? Do you understand that I'm stopping because now it's a partial sum? I'm going from 1 to n, where have I stopped? This is our partial sum here. So S sub n is, yeah, okay, start at 1, go to n. We've just done that. Now, step number 2. This is where it gets difficult. This is typically pretty easy. You just plug in some numbers, you go, and then you ultimately plug in n, no problem. Step number 2 is you got to find a formula for this. That's the hard part. Oh, sorry. Yeah, find a formula for S sub n. Find a formula for S sub n. So basically, you need to do this. What that equals, what the formula for the partial sum is, not just the terms in the sequence, okay? Look. This is the formula for the terms in the sequence. It's done, okay? It says that, hey, you want your 10th term in the sequence? It's 10. Hello, you should plug in 10, that's easy. What I want now is a formula for the partial sum, a formula for this crap. Well, does anybody know what the formula for that is?
And n plus 1, n plus 2.
Close.
N factorial.
No. We're downsliding.
Oh.
You're closer with the first one. You actually use these in your Riemann sums, if you remember those.
Yeah.
I think it's storied that Gauss found this out when he was like in elementary school or something. Pretty cool.
Wish I was
that
that
one.
genius.
He's super smart. He's really, now he's dumb, right? Because he's dead. He can't do no more math. Maybe, I don't know.
Maybe wherever he's at.
Wherever he's at. So this is our formula for the partial sum S sub n. So what we know is that S sub n is equal to n plus 1 over 2. You guys okay with that one so far? Okay, so what we've done is, all right, here's our series, no problem. It says series, we're adding it up. It says start with a list of your terms of your series. So we're doing okay. S sub n, our partial sum would go from 1, plug in 1, 2, plug in 2, 3, plug in 3, all the way till you plug in n. You actually have to have that nth term in there. Do not just leave this hanging with your ... Okay, end it with your nth term. Do you got me?
Yeah.
Now it says, okay, cool. Find a formula. This is the hard part. So finding this formula is the hard part. The rest of it's very easy. So once we find a formula, awesome. Here's what we've done. We've just done this part. We have that now. Now it says, I want you to determine what's going to happen as your n goes to infinity. So basically, if the partial sum for every term that you want is given by this formula, check it out. If I said, hey, find the partial sum for the first 6 terms, you just have to plug in 6. It'd be 6 times 7 over 2. Done. You guys with me on that one? Well, that's awesome. Now it says, find out what happens as n goes to infinity. So our step number 3 is really pretty straightforward. Step number 3 is just take a limit. As n approaches infinity. What this does is this makes our partial sum equal to our series. That's what that does. Check. This is why I asked you this very first question. I said, all right, now check it out. Are these two things equal? Are these two things equal right now with me covering this up?
No.
No, they're not. So this would equal this, but this would not equal that, correct? Because these two things are the same. So, if these two things aren't equal, the way I make them equal is I let this go to infinity, and that's where our limit is. So, as soon as we find our f sub n, just take your limit as n approaches infinity, and then if it converges, awesome, we found our sum of our series. If it doesn't converge, well, then we can't find the sum of our series. It's impossible to do that. Quick head nod if you're okay with that. Fun, right? So, step number 3 says, no problem, just take a limit as n approaches infinity of n plus 1 over 2. How much is that going to equal? Don't even worry about this, about doing a lot of math on this. How much is that going to equal? That's going to be infinity. That's infinity plus 1, right? That's infinity. What's infinity times infinity? Definitely infinity. Over 2? Who cares? Infinity. What's that tell you? Does the sequence, here's the perfect terminology, I hope that you're getting this. Is the sequence of partial sums convergent? Is the sequence, remember these are partial sums, right? Is a sequence of partial sums. Is a sequence of partial sums convergent? No, it's divergent. What that means is that when you get to the infinite term, the sum of that n equals infinity, you're going to get positive infinity here. Well, then what's your sum? It's divergent. We don't know. Because if our sequence of partial sums is divergent, that means our series is also divergent. So we'd say series, all that work for nothing. Series is divergent. I know we got very little payoff with that one, but I wanted to show you that not all series are divergent, but this is the way you go about it. Show of hands feel okay with that one? Good. All right. Can we move on to another example? Do you have any questions at all on this one before we get going? Yes? Am I explaining this well enough for it to make perfect sense to you?
Of course.
First time for everything, right? All right. So let's do more. I'm going to try to give you a whole bunch of different types of examples here because a lot of these things are done differently. Oh, sorry. I'm so used to X's. What should it be?
And
Yeah. For some reason, I really like these type of series. Some people don't so much. I do. So what I'm going to try to do is I'm going to try to see whether this series is convergent, and if it is, I'm going to try to find the sum. If it's not, then we're good to go. We're done. So I'm going to try to find the sum of this series. What's the first thing that I might want to do?
Combine the fraction.
find the partial sum.
Find the partial sum. So I'm going to try to find the partial sum. So the partial sum says, okay, well, the first thing that you better do, I'm going to write a little bit smaller than I normally do, because I'm going to need some space here. First thing that we do is we list out some terms here. So we better list out some terms. How do you find terms in a series? What would you do?
Plug in.
Yeah, because what a series is just a sequence added together. So let's plug in 1. If I plug in 1, I'm going to get 1/5. See where the 1/5 comes from?
Bless you.
Minus 1. Perfect. This would be n equals 1. That's our n equals 1 term. You okay with that one?
Mm-hmm.
What's the next thing I put?
N equals 2.
Nope, before that.
Oh, plus.
A plus sign, because it's a series. Okay, so let's keep on going. What's going to be our next two fractions? Can you tell me that? 1/7 minus 1/5. Very good. This would be n equals 2. What's the next thing I do?
Plus.
Very good. Can you come up with two more fractions here for me?
1/9 minus 1/7.
1/9 minus 1/7. Very good.
There's a pattern.
I love patterns. This is our third term. Show of hands, feel okay getting those fractions. So, hey, you know what? You plug in 1, you got it. You plug in 2, you got it. You plug in 3, you got it. Now, You need to do this until the nth term. So, basically, yes, you're looking for a pattern. Okay, you're looking for something you can make a formula out of. We're going to skip a whole bunch of them. And we're going to go to oh, what do I want to do? Yeah, I'll do that for you. I'm going to go to, shoot. Are you guys going to get super confused if I go down here and do dot, 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 and then plus down here?
No.
Okay, so line, just use your imagination. I want the n equals n minus 2 terms. I want the n equals n minus 1 terms. And I want the n equals n terms. Actually, you know what, by rights, because it's a partial sum, we could use this. We could use k. Really, that's what it should be, because our partial sums are k to n. So if you really want to be mathematically prudent here, you would do k. And then we do, oh, okay, because n equals n minus 2, that doesn't really make a lot of sense. We do k. And we do k. And we do k. Are you okay with that one? Reasoning behind it is because S sub n, the series from k equals 1 to n, that was our S sub n. Okay, that gave us an actual sum here. So really, when you're doing the partial sums, you should have your letters in terms of k. Are you seriously though? No pun intended. Are you okay with that? Okay. A-okay. Now the last one's. I'm going to work backwards here. The last one's really easy. If I let these go to just n, I'm going to have 1 over 2n plus 3 minus 1 over 2n plus 1. Do you see where that one's coming from? Now, if I have to find these guys, this would be 1 over, it wouldn't be 2n minus 3, it would be 2,
Bless you.
it would be 2, bless you, yes?
N minus 1 plus 3.
N minus 1 plus 3, very good. Minus 1 over 2n minus 1 plus 1. Notation's getting sloppy. There we go. Show of hands if you understand that concept, you feel okay with that one. Guys in the middle, yes, no? Are you sure? So this says, hey, you're plugging in 2, plug in 2. Plug in 3, plug in 3. Plug in n minus 1, you're plugging in n minus 1. Here it is. N minus 1 and n minus 1. That's all you're doing. Make sense? Now, if I want n minus 2, it would be what? 1 over what?
2 n minus 2.
Minus 1 over 2 n minus 2 plus 1. Ladies and gentlemen, are we all okay with that so far? If you didn't simplify your fractions, now's where you'd want to do it, okay? If you didn't simplify these things, now's where you'd want to do it. So I'm going to write these in purple. This is going to be just my fractions that are simplified. So we have 1 over 2n. Look at that. If you distribute that and you combine some like terms, how much are you going to get? 2n. Minus 1. 2n minus 1. You with me? Are you with me?
Yes.
This would be 1 over 2n. Do you see the minus 3? That one, come on folks, help me out here. 1, distribute combined terms. 1 over 2n, what is it?
Plus 1.
Minus 1 over
2n.
Please don't you give me 2n on this. Minus 1. Do you see where the minus 1 comes from? You can't just subtract 1, add 1. You have to distribute then combine like terms. Now this one, this is good to go. We're fine. Okay, quick show of hands if you feel okay with this so far. Would you be able to do this on your own? Of course you would. It's plugging in numbers. This says plug in 1, plug in 2, plug in 3. You got the fractions. This says plug in. I go backwards on these ones all the time. I plug in n. N's easy. Man, exactly what you got. Plug in n minus 1, plug in n minus 2, and simplify. Are there any questions on how we got those? This is important that you understand how we got those. Do you understand how we got those? Are you sure? Okay, so I'm not going to look here anymore. I don't want to look there. I'm going to look at these fractions, and I'm going to find out what in the world is happening here. Charles, you okay?
The second one, shouldn't that be on the bottom one where n, or 2n minus 1, both?
For this and this?
Yeah.
So negative 2 minus 2 plus 3.
Oh,
3,
sorry.
3 minus 2
Yeah,
is 1.
I
Minus 2 plus 1. I think we're right. I think we're good.
I put a 2 in there, sorry.
No problem. You okay with this? Now, obviously, we don't have every single term listed because we don't know what n is. Ultimately, n is going to go to infinity. That's why we had to include the n. You can't just say, let's go to 7. Okay. Well, no, because the limit wouldn't work there, right? Well, what's awesome about these types of telescoping series, you should be writing that, is that a lot of times, most of your terms, they're gone. Check it out. Now, when you're crossing these out, you need to follow the pattern. Please listen carefully to what I'm saying. Follow the pattern. It's crucial. Do you see anywhere else where you have a positive 1/5 and a minus 1/5?
Yes.
Look at the relationship amongst the terms. Here's how I do it. First fraction crosses with the last fraction in the next term. So, first fraction, last fraction, next term. Did you get that? First fraction, last fraction, next term. Did you get that? First fraction, it would cross out with the last fraction in the next term. Gone. Well, we've done the first one. Let's work backwards now, okay? Let's go backwards here. Let's look at this. Last term, our last fraction, crosses out with the first fraction in the previous term. Do you catch that one? Yes, no? Okay, well, last fraction crosses out with the first fraction in the previous term. That was the same pattern, only in reverse. First fraction cross out with last fraction next term. First fraction cross out with last fraction next term. Now here's the issue. First fraction would cross out with the,
Last fraction.
is this here?
No.
So this stays. There's nothing there. We stopped at n. I don't need the n plus 1 term. We stopped right there. Does that make sense to you?
Mm-hmm.
Now look at this one. Is this one going to cross out? Our last fractions, remember this relationship? Last fractions crossed out with the first fraction in the term previous. Last fraction would have crossed out with the first fraction in the term previous. It would be gone. Here's the last one. How about the negative 1/3? Last terms cross out with the first fraction in the term previous. Is there another fraction
No.
before this? So then, basically, this is so awesome. What are the only things that are going to be left in our partial sum?
1/3 and
Oh, no, it's not 1/3.
negative 1/3.
And?
1/2n plus 3.
Do you understand that every other fraction in this problem is gone? They all gone. They gone. They're all gone. Everything else, gone. Well, hey, look at that. Right now, we have a formula for our partial sums. This was step number 2. We created a formula for our partial sums. Isn't that kind of nice? If I say, I want the partial sum after the 10th term, here's what you do. You plug in negative 1/3, you plug in 10. Done. Done. That's it. Now, the question becomes, does this converge or does it diverge? What do you have to show for that?
Take the limit.
Just take the limit. This is now your formula. So in step number 3, we go, all right, well, let's take a limit of our partial sums as n approaches infinity. That means that we'll take a limit of our partial sums as n approaches infinity. Can you tell me, ladies and gentlemen, what's going to happen to my limit of this partial sum as n approaches infinity? The whole thing's 0? What happens to this?
0.
That's 0. What happens to this? Here's the awesome part about this. This goes back to the theory that we talked about at the very beginning. Not the theory, the work that we did, basically. Your partial sums are going to eventually end at negative 1/3. Does that make sense? and they don't really end, but they converge to -1/3. Well, because this is equal to our series, right now we know the series is equal to -1/3. That is awesome. It's very kind of interesting that when we add up all these terms forever, we still get -1/3. Jessica, you had a question?
Yeah, could you explain how the 1/2n minus 3 got crossed out again?
2n minus 3?
Yeah,
This one, okay, so did you notice how the 1/7, that's the last fraction, right?
yeah.
It's crossing out with the previous fraction, like a previous term. The 1/5 is crossing out with the previous term. This one would be crossing out with a previous term.
Oh,
Just
okay.
like this one did, just like this one did.
Okay.
Now, we don't go any further than this. That's our nth term. So this one doesn't get to get crossed out. This one doesn't because there's no previous term.
Okay.
That's the idea.
We just pretend like we have a term
Yeah.
dot.
This right here is called a telescoping series. Telescoping series. Happens like this very frequently, which is very nice for us because we can find a formula. So this is a telescoping series. Tell you what, let's do one more, just so you get a really good idea about what I'm going to be asking you for here. Some of you might not like this very much, but telescoping series really only work if you have a sum or difference of two fractions, typically a difference between two fractions. Do I have two fractions here?
No.
No, I don't. Now, if you're thinking, wait a minute, why don't we just take a limit of that thing? Remember that this right here is a sequence. It's just a sequence, and then when I add them the terms together, I get a series. So I can't just take a limit of this. Here's what the limit would tell me. The limit would say, the sequence of these terms exists because it goes to 0. The sum is not 0. The sequence converges. Therefore, the series is probably going to converge here. But we've got to show what the sum is. To find out what the sum is, we find the sequence of partial sums, and we take a limit. So the work is not over just by taking a limit. All that did for us was say whether the sequence is going to converge. I know the sequence of these terms would converge. The sequence of the partial sums, I don't even know, because I don't even know what the formula is for the sequence of partial terms. Now, because we know that telescoping series usually works with two fractions, I might be able to try to write this out and find a pattern to it for the series. But oftentimes it's easier to try to create something like that, a telescoping series. So what we're going to do, we're going to take this 4 over 4n squared minus 1. I'm going to try to factor that thing. This would be 2n plus 1, 2n minus 1. Actually, you know what? I think it does work out better if I do this. Easier to see. Let's do minus 1 plus 1. 2n minus 1, 2n plus 1. Does that look familiar to you?
Difference squares.
It is different squares, so we should know how to absolutely factor that. You guys with me on that one? Does this look familiar to you?
Yeah. They could turn it into two fractions.
How do I turn it into two fractions? Equals
2.
2?
A.
Okay, sure, 2. That seems right to me.
Hey.
We are geniuses. Does that work? No. Save the common denominator. Do you know what those numbers are? I know you can do it, but I don't know what those numbers are. Oh, crap. What's that? It never leaves you.
Partial
You're never free. You only think you're out of the matrix. Too bad we're not in linear algebra. You really would be in matrices. That would be awesome. You're never out of the matrix. Okay, so anyway, I'm going to go through this quickly. You should know how to do partial fractions, but understand that what a partial fraction will do for you here is decompose this thing into a couple fractions. Maybe those things are telescoping. Hopefully for us they will be. So we would have 4 equals a times 2n plus 1 plus b times 2n minus 1. Hey, can show of hands feel okay with our partial fraction here? Remember that the cover-up method, you go, okay, a 2n plus 1, b 2n minus 1, and then we start plugging some numbers in. Here's how I would do it. I'd say let n equal negative 1/2 and let n equal positive 1/2. The reason why I'm doing that, remember we're plugging in those numbers which make one factor 0. That's what we want to do. So if I have negative 1/2 here, this whole thing goes to 0. Do you see it? I would get 4 equals, if I have negative 1/2 here, I get negative 2b. And b equals negative 2. If I plug in 1/2 for n, 1/2 for n, 2 times 1/2 is 1, 1 minus 1 is 0, this whole thing's gone. 1/2 here, 2 times 1/2 is 1, 1 plus 1 is 2, 4 equals 2a, or a equals 2. What that means for us is that now instead of thinking of that series, I just decomposed my nasty fraction there into something that is hopefully telescoping. So series of 4 over 4n squared minus 1 is equivalent to saying the series n equals 1 to infinity, can't change that. What would our a become? What is that now?
2.
2 over what?
2 minus 1.
Plus,
Minus.
oh, minus, why minus?
Negative.
Because negative 2
Over?
plus 1.
Does that look a little bit better like what we've been dealing with so far? What's the next thing you're going to do?
Find the partial sum.
Partial sum, very good. So step number 1 is partial sum. How do you find the partial sums? What do you do? Plug in some numbers. Let's start. Where do we start?
1.
If I plug in 1, I'm going to get, oh good,
2 over 1.
I'll leave it 2 over 1. Minus what?
2 over 3. 2
Okay, let's plug in 2. 2 over what? Minus? Am I going too fast with my adding here? 2/3, okay, on to the next one. Let's
It's kind of slow sometimes.
2. Good. Okay. Let's do next one.
2/5.
K, remember this would be K. K equals 3. So 2/5 plus minus 2, hopefully 7ths. Do you guys see where those are coming from? They're odd numbers. This is a formula for odd numbers, so is that one. So you just plug in that, hey, look at that. 1, 3, 3, 5, 5, 7, blah, 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 blah. Do you guys get this?
Yes.
Yes, no?
Yes.
Now I'm going to jump down here again. I want the K equals n minus 1 terms. I'm not going to do the n minus 2 this time. I'm going to do the K equals n terms because this is a very straightforward series. When you're doing this, yeah, start off with 1, start off with plugging in 2, start off with plugging in 3. I always end with plugging in n first because it's easy to do. If I plug in n, I get 2 over 2n minus 1 minus 2 over 2n plus 1. You guys okay with plugging in n? It's just the ending terms of whatever this series says. Show of hands if you feel okay with that one. Now, let's plug in the n minus 1. If I plug in the n minus 1, we got 2 over 2 times n minus 1
Plus 1
minus 1. Minus 2 over 2 n minus 1 plus 1. That's 2 over,
2n minus 3.
perfect, 2 over,
2n minus 1. Minus.
okay, listen, I know I did the fractions very quickly. What I'm asking is, do you understand this idea of plugging numbers in and getting, it says specifically these two terms. Show of hands if you do understand that. Okay, now, this one's this, right? I'm not going to worry about this anymore. I'm worried about this. look for the pattern. What happens, please, this is the important part. You guys can do this, right? You can do partial fractions. You can do that. You can do this. Just plug in numbers in. Plug in 1, plug in 2, plug in 3, plug in n minus 1, plug in n. Stop there. Now look for the pattern. In your own words, what's the pattern?
The last first.
Last first. Cool, that works. Would this one cross out?
No.
There's no last. Would these cross out?
Yes.
These ones?
Yes.
This one?
Yes.
Okay, how about, let's see, where am I at? This one?
Yes.
Yes.
This one?
No.
Yes.
Yes.
Oh,
No?
yes.
Oh, wait,
The
wait.
N is the one that doesn't
Oh, it's
close.
the end. Oh, you didn't put that one.
Come on, bro.
That one. So inside, I called them insides, I don't know why. Insides, 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 insides. Last one, nope, there's no next one. So there's no first one, there's no last. So, yeah, outsides, whatever. So we'd have, what's left? I've got a 2, I've got a minus 2 over 2n plus 1. What's the last step, folks?
Limit.
And what's the limit of this?
2.
2 minus 0, sure, but don't forget that you have a 2 right there. Show of hands if that made sense to you guys. Middle people, are you guys okay with this? Are there any questions on this right now? So let's continue our talk about these series. Now the next thing that we talk about in our series is specific forms of series. So far we've talked about sequences, how to tell when they're convergent or divergent. Then we kind of use that idea of sequences to tell when series are convergent or divergent and find the sum by doing those partial sums. Remember, taking a limit of a partial sum gives us whether that series converges or diverges. Do you guys remember what we did last time, hopefully? Well, one specific series that we're going to get a lot is this thing called a geometric series. What a geometric series is a series of a very specific form. Like that, where you have a some constant times r some base raised to an n, raised to an expression in terms of n, where n is the index that's going 1, 2, 3, 4, 5, 6, 7 to infinity. So this is verify that's a series, firstly. Look at the terms of our series. The terms of our series would start with what?
1.
Well, it wouldn't be 1. It would start with a. If I plugged in 1, I'd get r to the 0, which would be 1. But then a times 1 would give us a. And then would add to it, what would add to it? What would the next term be?
AR.
AR. Very good. What would the next term be? Sure. And then the next term would be AR to the third, and it would never ever end because this thing's going to infinity. Show of hands if you're okay with that one. Very good, okay. Now, there is one other small change that we can do with this. You could have it this way, or you could have, and you can verify this is the same thing, or you could have a series from n equals 0 to infinity of AR to the n. Can you verify that those two things are the same series for me, please?
No.
If I plug in 1, hey, I start with r to the 0. If I plug in 0, I start with r to the 0. It's the same exact thing. So this will give us exactly the same thing. What I need you to know is that both of these expressions stand for geometric series. So far, so good? Now, I'm going to prove something in just a bit, but I want you to know a couple things before I prove it. First thing, geometric series converge when you know what, you could probably think critically about this, and you could probably tell me. Geometric series converge when A is basically meaningless as far as convergent or divergent. It's a constant. It will not change anything about this. You can actually pull the A all the way out front and be fine with it and multiply later, okay? We're going to find out in our properties at the very end of this section that we could actually pull A out and be fine. It's a constant. Tell me something about R. These series are going to converge when R is what? Less than. One's kind of a big number for us as far as series go. Imagine if R is 1. If R is 1, then I'm going to go A plus A plus A plus A plus A plus A for infinity. If I do that forever, I'm going to end up with infinity. It's basically infinity times a constant. Does that make sense to you? If R is bigger than 1, R is bigger than 1. I'm going to go A, then something's going to be bigger than that. Then something's going to be way bigger, and then way bigger. It's going to go to infinity, if it's positive, or maybe negative infinity, I don't know, but it's definitely going to diverge because my number's going to go bigger or way smaller, and bigger and then way smaller if it's alternating or something like that. So here's the deal. This is going to converge when R is less than 1 in terms of absolute value. What that means for us, we can think about it another way. R's got to be between two numbers for it to converge. What two numbers does it have to be between? Yeah. If you didn't think, it's not just simply less than 1, it's actually between -1 and 1, because if you had an R being like -4, do you see that if I had R -4, when I square it, it's going to be huge. Or, well, not square it, huge, but when I square it, it's going to get really big. When I cube it, it'll get really big negatively. And then when I take it to the fourth power, it become positive again. Does that make sense to you? So the whole thing about geometric series is, well, if you're going to add up these terms, the only way that they're going to add up, the only way that you're actually be able to find a sum, is if these terms keep getting smaller and smaller and smaller. Basically, it's got to be decreasing. Does that make sense to you? In terms of absolute value, it must be decreasing. Well, the only numbers that do that, the only numbers that decrease when I take them to larger and larger powers, are fractions. That's the only ones that do that. And so what this says is that our geometric series, yeah, they can converge, but they can only converge if the absolute value of R is less than 1. Not equal to 1. We already talked about equal to 1, right? If they're equal to 1, then you're going to keep on adding A forever. It's going to grow without bound. Absolute value less than 1 is the same thing as R is between -1 and 1. Also, what's very cool about this, oh, but you know what, I can say this little corollary here. It will diverge if R is greater than or equal to 1 in terms of absolute value. What's also really nice is that we have a built-in formula for the geometric series. I'm going to prove this to you in just a bit, but I'm going to give it to you now. Here's our formula. If you know that you fit the form of a geometric series, so basically if you know you have a constant times some number raised to the n-1 where your R in absolute value is less than 1, you can find the sum of it. And the sum's really, really nice. So here we go. The sum is A over 1 minus R. That's it. You can always find the sum to these. So converges when the absolute value of R is less than 1, diverges when the absolute value of R is greater than 1. Would you like to see the proof for this, why this actually happens? Okay, let's do that. So here's what I'm going to do. I'm going to start with just my general geometric series here. And what we learned last time was that if I want to find out what the sum is, or if I want to find out whether this series converges, I'm probably going to be looking for a partial sum first. Remember talking about the partial sums last time? Look for a partial sum first. So I'm going to look at S sub n, my partial sum. Well, what my partial sum is going to be is this. We already actually have a partial sum up here already. We got, if I start with, help me out again with this. If I start with 1, what am I going to get?
A.
And then if I go with the next term, I'm going to get, and then I'm going to do AR squared, and then I'm going to do AR cubed, and I'm going to do AR. Now here's the deal. A partial sum ends. A partial sum ends at n. Does that make sense to you? Ends at n. So here's the deal. Listen carefully. If I plug in n, will my last term be A times R to the n? Will that be my last term? No, because if I plug in n, you know what? I plugged in 1, I get 0. I plugged in 2, I get 1. I plugged in 3, I get 2. I plugged in n, I get n minus 1. Naturally, hopefully you see that, this has to be my last term. It's got to be A times R to the n minus 1. Show of hands if you're okay with that so far. Awesome. Now, I'm going to do some kind of fancy pants math here. What we're going to do is we're going to create another expression and then subtract these two things. We're going to be a little bit fancy about it. So what I'm going to do, I'm going to multiply it because you do believe this, right? This is a partial sum. Well, it's an equation too, which means that I can do whatever I want as long as I do it to both sides. I'm going to multiply both sides by r. So I'm going to have r times s sub n equals, if I multiply both sides by r, understand that I would have to distribute to every single one of these. Do you guys see that? I distribute to every single one. That means I'm going to have ar plus ar squared plus ar cubed plus the very last term. What would the very last term become when I multiply it by r? Very good. I'd have one additional r. Notice if I multiply this by r, it would be ar n minus 1 times r to the first. You add exponents when you multiply common bases, that would be ar to the n power. Quick head nod if you're okay with that one. Now here's what we're going to do now. This is kind of cool. You believe this expression, right? Just a partial sum, no problem. We actually had some of that on the board. We're just stopping because you say partial sum goes up to a certain value of n. That would be n. We got our ending term here. This is a partial sum. Multiply both sides by r, we get this one. And now we're going to subtract these guys. If I subtract them, what we end up getting is s sub n minus r times s sub n equals, so I'm subtracting this minus this. I'm going to erase these r's here. Basically, we're just multiply by r. That means you got to multiply this by r. Okie dokie with that one? Now we're subtracting. S sub n minus r sub s sub n. Got it. That means we're going to have to take this stuff and subtract all of this stuff. What's going to happen with most of these terms?
Cancel.
Yeah, in fact, what's the only couple terms that don't cancel?
A.
A doesn't, because there's no a down here. So a, r, okay, squared, cool, boom, boom. A doesn't, and what other one doesn't? What about that one? Is that one going to go away? Yeah, that one's going to be here somewhere. Does that make sense? That's going to be here somewhere, because what would happen is I'd have the a sub r, a times r to the n minus 2, and when I multiply by n, that becomes n minus 1, and that would go away with this one. So this is gone. I'd have this one now.
It would be a negative.
Oh yes, I'm sorry. I wrote plus. Yeah, we are subtracting. Good call. Good catch. I would have caught it in about 5 seconds, but I saw that. I don't know why. So yeah, we'd have this minus this. Well, okay. Well, this a stays. Minus 0, minus 0, minus 0, minus 0, but then subtract that last one. Patrick's right, we get minus a times r to the n. Show of hands, feel okay with that so far. Now here's what we're going to do. What we're going to do right now is we're going to solve this for s sub n. What that means is we're going to factor. If I factor out my s sub n, I get 1 minus r. If I factor out my a, I get 1 minus r to the n. Still okay with that? One last step, let's just divide by 1 minus r. Are you so far so good on this? Now here's the interesting thing. We started with a partial sum of our geometric series. I've worked it out mathematically to say this is still a formula now for the partial sum of our series. Basically, all we've done, we've made a formula out of this. Does that make sense to you? Made a formula. Well, here's what we learned last time. Last time we learned that if we want to see whether this series converges, what we would do is we take a partial sum and we do what with it? Limit. As n approaches what? Okay, if you're confused, back the video up or go and watch this video again. Here's what we learned last time. We learned that if you want to find out whether a series converges, find a partial sum. A partial sum ends at n, correct? But then what you do is you say, hey, now let the n go to infinity. And then your partial sum translates to your series. If you let this, the limit of a partial sum as n approaches infinity is your series. So this is what we had. I'll write everything out for you. This is equal to the limit of your partial sum. This was last time. Okay, this is not new stuff. This is true. This says if you find a partial sum for this guy and you let that n go to infinity, That's true. However, we already know an expression for this. I don't want this one. That's nasty, right? I can't do a limit of that. That sucks. What I can do is a limit of this thing, though. So now that we've worked down to, hey, your partial sum is this, let's just take a limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. Now I want to think really carefully about this. What is changing and what's going to be a constant in this particular case? Firstly, tell me what a is. A is a constant. R, the number r will be fixed depending on what your series is. So it will be something like 1/2, something like 4/3, something like 7, whatever, negative 3/4. Whatever that is, your r will be fixed. Do you understand that? The only thing that's moving here is your n. N's going towards infinity. Now here's the whole point about why this is the way it is. I want to give this to you first, that way you understand here what's going on. Okay, let me full attention here. If r is 1, this would be 0 over 0. That would be a big problem for us. We would have a limit that does not exist. Therefore, we would get diverges when r equals 1. Does that make sense to you? It's clear that it will, because if you plug in 1 for all these things, you're going to get a times infinity. There you go. Now, let's say r is more than 1. If r is more than 1, so like a number like 2, what's 2 to the infinity? It's infinity. That's where this comes from. If your r, in absolute value, is more than 1, you're going to get something that is infinity here. When's the only time in the world you can take a number and take it to the infinity and it's going to give you 0?
It's less than 1.
What's less than 1? When it's a fraction. That's what this is coming from, okay? It says, hey, you know what? If you take a fraction less than 1, so this equals 0 if absolute value of r is less than 1. That's where this is coming from. I'm going to try to go through it one more time for you so you really do get what's going on. Do you get what's going on already? A little bit? What's going on is that this is our partial sum no matter what we have for r. Does that make sense to you? I've proven it right here. This is our partial sum for our series no matter what we have for r. However, if we have r for certain values, we're going to get two different outcomes. If r is 1 or more, we get divergent because this thing is going to infinity. Are you with me? We get infinity over constant number, because r is a constant. Infinity over constant is infinity, it's divergent. If we have r less than 1, though, in absolute value, so between negative 1 and 1, between them, well then, that number raised to infinity, well that's going to go to 0. 1 minus 0 is, a times 1 is, r is a constant here, we have a over 1 minus r. And that is proving two things here. It's proving two things. Three things, really. It's proving that this series diverges when r is more than or equal to 1 in terms of absolute value. It's also proving that the series converges when r is between negative 1 and 1, so absolute value of r is less than 1. And it's also proving that the sum is equal to this, because when we think back to the last thing we did in this class, last time, it said that when you find out the limit of your partial sum, your partial sums are a sequence, and the ending sequence would be when n's infinity. The ending term of your sequence is still a sum. It's the sum at infinity. So we said this. If your limit exists, your series converges. More than that, because you're finding the limit of a partial sum, if your limit exists, it also is the sum of your series. It's also what this thing is. And we just proved that. Show of hands, you feel okay with that one. Now, do you want to see some examples?
Yeah.
You're going to like these. You really are. Promise. Now, in order to use this stuff, you first have to determine whether this thing is actually a geometric series or not. So we're going to look at it. Is it of the form of a geometric series?
Yes.
If it is, and here's how you check. Here's how you check. Your first exponent should be 0. It should match up with 1 and n minus 1, or 0 with n. Does that make sense? Those are the two options that you have in this class. So 1 and n minus 1, 0 and n. It should have a constant, if any, and it should have some number being raised to that power. So in our case, we should have an a. You should be able to tell me what the a is and what the r is. So tell me, what's the a, please?
3.
3. Very good. Does the a have anything to do with convergence or divergence? No. Tell me what the r is. Does the r have anything to do with convergence or divergence? Oh, heck yeah. That's why we did this whole thing. So you tell me, is this geometric series going to converge or is it going to diverge? How do you know it's going to converge? That's right. The r is between -1 and 1. Or the absolute value of r is less than 1. Not a problem. So because we have just proven this, what we know is that this series converges. Did we have to do any work with that? Nice, huh? Series converges. And you should be able to tell me the sum. The sum is, this is the sum right here. All we got to do is plug the numbers in, guys. It's that simple. What's our a again?
3.
Over. It should be 1 minus r. Be careful on your signs. Don't screw this part up. 1 minus what?
Negative.
Perfect. 3 over 1 minus -1/2. Show of hands if you feel okay with where those numbers are coming from. Now, can you do 3 over 1 minus -1/2?
Yes.
Sure. That's how much? 3 over 3 halves? Or
2.
sure, 3 over 1, reciprocate, multiply, we get 2. So we know a couple things. It's kind of interesting, right? We know a couple things. Firstly, I know because this series is geometric, and we already prove it, we've already proven it, because our r is less than, in absolute terms of absolute value, is less than 1, I know it's going to converge. More than that, I can plug my numbers in. Make sure you don't use +1/2 here. You will get a different sum, okay? You do have to plug in what the actual r is. Plug that in. Here's our a. Here's 1 minus r. Figure it out. More than that, we know our sum is 2. And that's really all we got to do with geometric series. What if this -1/2 had been a 4/3? Would that be a convergent geometric series or a divergent geometric series? Why? What if it was -4/3?
Or below -1.
Would it still be divergent?
Yes.
Absolutely. The absolute value of 4/3 is still 1/3. It's still more than 1. So in those two cases, we'd get something that would be divergent. We wouldn't have to. Now listen, here's the whole thing, okay? Here's the whole thing. If you find that your geometric series is divergent, should you find the sum?
No.
Heck no, it's divergent. Notice though that the formula will let you find the sum, won't it? You can still plug in 3 and you can still plug in -4/3 and it will still give you an answer. Is the answer going to be right?
No.
So don't do that. Okay? You first show convergent, then you find the sum. You do not do it the other way around. You don't find the sum and say, hey, the sum is this, but the series diverges. That does not make sense at all. Okie dokie. So show convergence, then find the sum if it's appropriate. Does that make sense to you?
Yes.
So this one, this right here, this would be divergent. Therefore, this would make absolutely no sense to do. Let's move on. Sometimes we got to do a little bit more work with these guys. I'm going to show you one of those. Let's say we don't have an explicit a sub n. Right? It's not given to us. All we know is that this thing is 5/3 plus, I'm sorry, minus 5/9 plus 5 27ths minus 5 over 81, plus so on and so forth. So it's alternating signs. We know 5 is always on the numerator, and we're going 3, 9, 27, 81. I'm going to show you a couple ways that we want to work with this. Number one thing, notice where our series is starting. Where's our series starting, at 1 or at 0? Starting at 1. What that means for you is that my exponent has to be n minus 1. Does that make sense to you? You've got to match it up. It's got to be 0 with n, or it's got to be 1 with n minus 1. Now, you just heard me, understand that. So I'm going to be going to find an exponent of n minus 1 for my r. Now, how we do that? Well, try to factor and simplify as much as you can to find that pattern. So for instance, I would factor out the 5. I would also factor out the 1/3 from this, and here's the reason why. What I want is for my first term to be 1. Okay? The reason is because I'm going to take something to the 0 power. Does that make sense? So if I leave it as a 5 and then a 1/3, does something to the 0 power give me 1/3? No. But if I factor out the 3 as well, does something to the 0 power give me 1? Then yes, that's what I want. Does that make sense to you? I'll say that one more time. When you're finding your series, if you start at 1, you're going to want to have an exponent of n minus 1. That's one thing we need to know. Second thing, because I'm going to have an exponent of n minus 1, my very first term inside my parentheses should be 1. Because when I do 1 minus 1, it's going to give me 0 for my power. Anything to the 0 power is 1. That's what I need to have happen. Now, I'm going to be a little bit more pattern-oriented for my next part of this. Instead of like something like minus 1 over 27, I'll think about this as 3 to the 3rd. Instead of 1 over 9, I'll do 3 to the 2nd. Instead of 1 over 3, I'll do 3 to the 1st. Instead of 1 over 1, I'll do 3 to the... Aha! Do you see what I'm talking about the first power's got to be 0? This is what I needed. If I would have left this as 3 to the 1st, I would have had a little bit of a problem here, because there'd be no way for me, not a real good way for me to reconcile, I start at 1, but I'm getting a 0. Does that make sense? If I started at 1 with a 1, well, I'd be off by a negative if I did start at 0 with a, 1 with an n. I'd be off by my sign. So we do got to factor out that 5/3, not just the 5. Well, here's what's going on then. What's going on is I have 5/3, and I have, look at this. This is to the 0 power, to the 1st power, to the 2nd power, to the 3rd power. This is 1/3 to... Now we're very close. Let's see if it works firstly, okay? Let's see if it works. I started at 1, right? So I need an n minus 1 power. It's got to match up. If I do that, if I start at 1, my first term would be a 0, 1/3, 0. Then I get 1 over 3 to the 1st, then 2nd, then 3rd. Are you guys okay with this so far? Now here's the problem. I'm alternating. How do I fix this? Negative here. If I put a negative right there, well shoot, let's make sure that this works, okay? 5/3 would be there no matter what, correct? Then my series would go through, if I plugged in 1, I would get 1 minus 1 is 0, I would get 1 out of that, that's here. If I plugged in 2, I'd get 2 minus 1 is 1. I'd get my negative back, I'd get my 1 back, I would get my 3 to the 1st back. If I plugged in 3, I would get 3 minus 1 is 2. I would get a positive, I'd get a 1, and I get 3 squared. Do you see that this is our pattern? This is our series now. Well, that's kind of cool because now I know that this thing equals this thing. 5/3, negative 1/3 to the n minus 1. Can you tell me now what type of a series that is? Go ahead and you discover if it's convergent. If it is convergent, find the sum. If it's not, then say it's divergent. Stop right there. Go for it. So if this thing is a geometric series, we should probably be able to figure out whether it's going to be convergent or not just by looking at it. Is this going to be convergent, yes or no? Yeah, it's geometric. It's a geometric series with A, what's our A?
5/3.
What's our R?
Negative 1/3.
Good, negative 1/3. Is that between negative 1 and 1?
Mhm.
Then this thing is going to be convergent. That's the first thing you say, okay? This converges. Then we find out the sum. The sum of this series is, how would you find out the sum?
A over 1
Sure. A over 1 minus R. Did you guys do that as well? 5/3 over 1 minus negative 1/3. How much is that all said and done? 5/3? 5/4. Okay. So our sum is 1 and 1/4. How many people found it? Are you guys okay with this so far? Easy, medium, hard? Pretty easy, as long as you can get down to here, right? Once you get to here, I mean, this is a piece of cake. This is awesome. Just don't do silly things. Don't find out that it's convergent and then find things like sums. That would be silly. Find out whether it's convergent or divergent first, and then if it converges, find the sum. Let's do one more. You see, sometimes these things aren't that obvious that they are geometric series, like that one. Does that look like a geometric series right now?
No.
Heck no. But sometimes you can manipulate it well enough. Now here's the thought process. You need to focus on this one because this might leave you in the dust if you're not, okay? Geometric series match up n equals 1 to a power of n minus 1. Do you get that? Or it'd be n equals 0 to a power of n. Now, if we know that, then a lot of times we can manipulate our series to see if it's going to be geometric. For instance, here's what I would do. Instead of e to the n, I'd try to force this thing to have an exponent of n minus 1. Can you verify for me that e to the n is e times e to the n minus 1? Okay. Now, this is 3 to the n plus 1. What I know is that 3 to the n plus 1 is 3 squared times 3 to the n minus 1. Can you verify that for me? Yes, no? Okay, because when you multiply common bases, you add those powers, right? So if I had 3 to the second times 3 to the n minus 1, it'd be 2 plus n minus 1 as my exponent. That would be 2 plus, no it wouldn't. It would be n plus 1. That would be my power there. Show of hands if you feel okay with that one. Guys over here, are we okay with that? You sure? Okay. Man. Hey, quick question. Can I separate fractions by multiplication?
Yes.
Multiplication? Is this a constant? That's e over 9. This is e over 9. Times e to the n minus 1 over 3 to the n minus 1. Tell me something about e to the n minus 1 over 3 to the n minus 1. What could I do with that, maybe? I could make one fraction to a power, couldn't I? Because both my numerator and denominator have the same power. Then this thing is the same thing as a series n equals 1 to infinity of, okay, e over 9, that's fine. It's ugly, but it's fine. And then I'd have e over 3 to the n minus 1. Now, we are practically done with this problem, but I want to walk through it one more time to make sure that you guys get what we're doing here. First thing we're doing, we're checking to see if it's geometric. We're looking at it saying, hey, can I make it into something that's geometric? If I can, I need to look with where my n starts. If my n starts at 1, I need to match this up to a power of n minus 1. Did you guys get the first step? Yes, no?
Yes.
Then try to start doing that. Say, well, wait a minute, then e to the n? No, I don't want to the n. I want to the n minus 1. Let's split off an e. So if I go, all right, well, e to the n, I don't like that. I want to think about this as e to, it's close, but it's not. As e to the n minus 1 times e to the first. Because if I add those together, I still get e to the n. Now, of course, I have it written backwards, but this is the idea. Try to find out the appropriate power from our expressions here. E times e to the n minus 1, no problem. Same thing with 3 to the n plus 1. Well, 3 to the n plus 1 is 3 times 3 times e times 3 to the n minus 1. That's 3 squared. This is a constant. Pull that off. This, I can rewrite that because they have the same power as e over 3 to the n minus 1, and all of a sudden we have this thing that is a geometric series with an a of, what's our a? E over 9. It's weird, but it's e over 9. What is our r? Now, you tell me, is that going to be convergent? Is that going to be divergent? You better know how much e is before you make that statement, huh? It's about 2.71 or so. So, is this going to be convergent or divergent? Yeah, hey, look at this. This is less than 1. Not a problem. So this is going to be convergent. If we want to find our sum would be a over 1 minus r. Well, let's do a little bit of fraction work. We'd have e over 9 over, if you want a common denominator, that's 3 over 3 minus e over 3. That's going to be e over 9, 3 minus e over 3. Reciprocate and multiply. We get e over 9 times 3 over 3 minus e. If we simplify, we get e over 3 times 3 minus e. It's just some fraction work, but that's how we do it. That would be our sum right there. It's a weird sum, but what I'm asking is that a constant? Is that a number? Sure. Could you find out an approximation on your calculator?
Yeah.
If you really wanted to, you could do that. Ladies and gentlemen, how many of you feel okay on getting down to this step at least? How about determining whether this is a convergent or divergent geometric series? Can you do that? Do you see where all this junk came from? Then you know all you need to know. Okay. The next thing, Rob, you have a question? The next thing we're going to talk about is a different type of series. We're going to talk about the harmonic series. Most of what I'm going to tell you right now, you're just going to write down as notes, but they're very important notes. First thing, this is what the harmonic series is defined as. The harmonic series would be this. If you look at the series, if you start plugging in 1, and then 2, and then 3, and then 4, you're going to get 1 plus a half, plus a third, plus a fourth, plus forever and ever and ever. 1 half, 1 third, 1 fourth, 1 fifth, 1 sixth, 1 seventh, 1 eighth, 1 ninth, 1 tenth, and so on 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 forever and ever and ever and ever. You guys okay with that one? Now, you would think, because this is positive, and because it's decreasing, because it's doing that you would get a convergent series. You do not. The harmonic series is divergent. I won't prove it to you. The proof is in any calculus book that you find. It's not that hard. I think you can follow it. The harmonic series is actually divergent. This series diverges. Now, there's a couple things we learn out of doing the proof on this thing I'm going to give to you. First one is this. They're very interesting concepts I want you to know. First one is this. If a sequence we're going back to sequences for a second. If a sequence A sub n is convergent, any subsequence of A sub n must also be convergent. Does that make sense to you? I say, hey, here's this gigantic sequence. This gigantic sequence converges, we know that. If I cut a little bit off of it and say, now let's just look at the inside part of it, can this possibly diverge when the whole thing converges? That doesn't make sense at all. So, if the sequence converges, any subsection, subsequence of it must also be convergent. That wouldn't make sense otherwise. You can't have that. Now, the corollary of this is this. To show. What that means is the corollary, think about it this way. Let's say that you had a gigantic series that you didn't, listen carefully please, that you didn't know was convergent or divergent. Let's say you didn't know, that's the whole thing, okay? Now let's say you consider just a subsequence of that sequence. If you find out that that subsequence is divergent, what's it tell you about the whole sequence? It has to. There's no way for a little part to be divergent and then come back, oh, but the rest is convergent. That doesn't make sense. Okay? So if a part of your sequence, if a subsequence is divergent, the whole sequence is divergent. So, to show divergence, to show that a sequence diverges, it is enough to show that a subsequence diverges. That's actually what they do with the harmonic series. On the harmonic series, you take a subsequence. You show that subsequence is divergent to infinity, but just the subsequence of it. It's divergent, therefore the whole sequence diverges. Do you guys understand these two statements? Hey, if a sequence is convergent, every subsequence has to be as well. Therefore, if a subsequence is divergent, the whole thing has to be divergent. So, sequence converges, all subsequences have to as well. But if a subsequence diverges, the whole sequence must be divergent as well. A couple more notes for you. Actually, you know what? I still got some room. So more notes. You know what? I'm going to write over here because it's really... Never mind. The reason I give you this one about sequences is because we actually use that for the partial sums of the harmonic series. It's the way we prove that it's divergent. We're going to go back to series right now for some more notes. These stem from a lot of these ideas. If a series converges, then the limit of the sequence of terms has to equal 0. What this means, I hope that you grasp onto this. Please listen carefully. You remember talking about sequences and how when you take the limit of a sequence, if the limit of the sequence equals a number, then it converges, and if it doesn't equal a number, then it diverges? Remember that? Well, think about this now. It's not just that we have the ending terms of our sequence being numbers, it's that we're adding them together. So, if your listen carefully because I don't want to blow your heads up, okay? If the limit of your sequence goes to a specific number that's not 0, do you understand that you're always going to be adding more of that number? So if the limit of your sequence ends in like 5, oh, okay, great. Your sequence converges. But then for infinity, you're going to be adding 5, plus 5, plus 5, plus 5, plus 5, plus 5, plus 5. What's the only number that you can keep on adding and it doesn't add to your sum?
0.
That's what that says. It says that in order for your series to be convergent, in order for this to happen, if this happens, if your series is convergent, then what must have taken place was that the limit of your sequence of these terms eventually has to go to 0. You have to end by adding terms that are 0. Show of hands if you understand that concept. That's the idea here. Now, What that means is that, to show a series diverges, it's enough to show that the limit of your sequence of terms does not equal 0. If the limit of your sequence of terms from which you are getting your series does not equal 0 or does not exist, the series from which we're the series upon the series that we're basing upon our sequence of a sub n terms diverges. Here's the problem that students have with this. Here's the problem that students have. The problem students have is they think that this is a biconditional statement. They think that if the series converges, the limit equals 0, and if the limit equals 0, the series converges. That is not true. I'm going to say it right out, flat out, that is not true. Sometimes it happens, sometimes it doesn't. Here's what I'm going to tell you. I'm going to go through it one more time, so I'm trying to be very clear here with you. If you know, I'm going to speak louder so you really hear me. Doesn't mean you're going to understand it more, but you're going to hear me. If the series converges, the limit of your sequence from which you're getting your terms for your series has to be 0. That has to happen. Because you're adding terms which are going to 0, 0, 0. It is not true that if the limit of your terms equals 0, of your sequence, that the series is going to converge. Prime example right here. The limit of 1 over n is 0. Does the series converge? No. The series diverges and it can be proven. I didn't prove it, but it can be proven. So, if we want to show convergent, we don't just do this. We don't. But, if we want to show divergence, you go, okay, well cool. If it converges, this has to happen. So if this doesn't happen, it will not converge. Does that make sense? Mm-hmm. So we can do that though. We can say, cool. So it's enough to show a series diverges, it's enough to show this happens. So if the limit of our terms does not equal 0, then what that means is we're not adding 0 at the very end of our sequence. We're not adding them together. We're adding numbers. That goes forever and ever. We're going to always add up numbers more and more and more and more and more that are the same, okay? Or close to the same. Or it doesn't exist, then this series has to diverge. That's what we can do. Let me say that one more time. So, big note. Limit equals 0 does not necessarily, I think I spelled that wrong, mean convergence of your series. It does not necessarily mean convergence of your series. You know, I was going to say one more thing, I completely forgot what it was. Dang, totally forgot. It was important too. No, it's not good,
Looks
right?
like we can't do our homework.
Yeah, too bad. It'll come to me sometime. Okay, so if the series converges, this has to happen. If this happens, it does not necessarily mean your series converges. But if you want to show that your series diverges, just show that this doesn't happen. Does that make sense to you? This is like a condition. You got to have this and something else for it to be convergent. So if this doesn't happen, bam, your series diverges. This right here, I know what it was. This is called the divergence test. So if they're asking you, hey, do the divergence test, all you got to do, take the limit of your terms. Please listen carefully. If the limit of the sequence from which you are getting your series, if the limit of your sequence does not go to 0 or does not exist, what do you know about your series? If the limit of the terms of your sequence do go to 0, what do you know about your series? It might not diverge.
Okay.
Michael.
So this is due Thursday?
Okay, there's one more thing we gotta do. It's super, super easy. Let me show you an example of this first. I'll show you the one more thing we can do, and then,
That's a wrap.
well, you gotta see this one time, okay? At least this. So we're gonna use the divergence test real quick. And when I mean real quick, it's gonna be real quick. Here's your series. Here's how you show whether it's divergent or maybe not. You take the limit as your terms approach infinity of the terms of your series. That's a sequence. The terms of your series is a sequence. So you take basically the limit of your sequence. How much is this limit? 2/3. It's 2/3. That's what it is. Because you divide by the largest power in the denominator, do L'Hopital's rule twice, whatever it is, simplify, you get 2/3. Is this equal to 0?
No.
What do you know about that series?
Divergence.
Divergence. Here's why. Because at the very end, when you get towards infinity, you're going to be adding fractions together that are of the value 2/3. So 2/3 plus 2/3 plus 2, that eventually will still go to infinity. Does that make sense to you? That's the whole idea. We have one more thing to do. It's about 5 minutes. I'm not going to do it now. Don't worry. But next time, we have a little bit more to do on this section. So the last little bit, section 9 point, whatever we're on. We're going to talk about properties of convergent series. Like I said, we're going to do just maybe 1 or 2 more examples. So the first thing I need you to know is that if we know that our series is convergent, or so basically if we're testing for a convergence, what we can do with it are these 2 properties. If we ever have a series with a constant being multiplied by the sequence from where we get our series, so like our a sub n, we can always pull that constant out in front of our series. So instead of having a series of c times a sub n, it's the same thing as doing c times the series of a sub n with no problems. Also, what you need to know is that if you have a series where you have 2 sequences added together that are giving you the terms of the series, or subtracted, so added or subtracted, you can split up those series by the sum or the difference. So if we have a series that's of 2 sequences added together, we can have a series of the first sequence plus a series of the second sequence. That's the idea. You guys okay with that one? And oftentimes this will really help you on determining whether or not your series are convergent or divergent. And if they are convergent, it'll help you to find the sum. So let me show you with this one final example, and then I'll show you that shortcut I was talking about. So first thing, do you see anything that fits our 2 properties that we have? What could we do here?
There's subtraction.
Yeah, we could. In fact, if you think about this, we could separate the fraction. We could have 2 to the n over 3 to the n minus 5 to the n over 3 to the n, and then separate those series. Does that make sense to you?
Yeah.
So we could do this and say, all right, well, cool. This is n equals 1 to infinity of 2 to the n over 3 to the n minus 5 to the n over 3 to the n. That works. We can always separate fractions like that. And then because I have one sequence minus another sequence inside of my series here, I can separate that series. Now that we've separated our series, we can actually start looking at each one and seeing whether they're convergent or not. Let me make one statement about this, please, before you keep going on this. Listen carefully. Our original series was this one, correct? So if we split it into parts, if we split it into these parts, I don't care how many there are, if we split it into parts, tell me what has to happen with each part to make sure that this whole thing is convergent. Tell me what has to happen.
All of them have to be,
Say that louder.
all of them have to be convergent.
Very good. Each part must be convergent for the whole thing to be convergent. Does that make sense to you? You can't have one thing add to infinity and the other thing add to a number and go, oh, therefore this thing adds to a number. That doesn't make sense. So if any one of these parts is divergent, The whole thing is divergent. Does that make sense to you?
Yes.
What that means is that if you're smart about this and you see one part that's definitely divergent, oh yeah, you're done. Does that make sense?
Yeah.
I mean, why would you go through the process of finding the sum of one thing if you know the other thing's going to be divergent? Rob, you question?
Suppose they're both convergent, will they arrive at the same number?
These won't be the same number, but you can add them together to get this series. That's what this whole thing says. Okay, it says the series of a sum is the sum of two series. The sum SUM will be the same if you add them together. If they were both convergent. Does that make sense to you? So here we go. If we did this, one thing that we could do is we could make this a series n equals 1 to infinity of 2/3 to the n minus the series of n equals 1 to infinity of 5/3 to the n. Can you explain to me why I'm putting it in this format?
Geometry.
That's a geometric series. Yeah, if we have a geometric series right now, we can tell immediately whether these things are convergent or divergent. Now, there's one thing that's wrong with this picture. Do you see what's wrong with this picture as far as my series are concerned? No? One of us does. I know one of us does. One of us sees, I see what's wrong. Two of us then, because one other person said, I know what's wrong. Maybe they're lying, I don't know. But let's see if you know what's incorrect. I told you that with geometric series, in order to find the sum correctly, your powers have to match up. Your index and your powers have to match up. Listen, in order for the sum formula to work, remember the sum formula was A over 1 minus R? Do you remember that at all?
Yeah.
In order for that to work, your first power must be 0. Is your first power 0?
No.
Okay, so this formula won't work correctly. Now I'm about to give you a shortcut in about 5 minutes on how to get around this, all right, without doing a whole bunch of work. There's 2 ways really. But even if it doesn't match up exactly, you can still tell me whether it's convergent or not, because this R will not change even though I strip off a fraction and make my power go down 1. So here's my question. Let's suppose my R is 2/3. Would this be a convergent series, yes or no? 2/3. Let's say this is 5/3. Would this be a convergent series, yes or no? No. So automatically we know this is divergent. Now let's assume that they're both convergent. Here's what you would do. To get my powers to match up, I would split off one power, and then that reduces my exponent by 1. Does that make sense to you? You sure? This is the same thing as that, but now they match. Hey, now it's a geometric series the way we like to see it, where our powers match. If your powers match up, basically match up means when I plug in my first number, my first n, when I plug that in, this power is 0. Please listen very carefully here. If the first power is 0, then A is actually the first term in my series. Do you understand that?
Yeah.
This is always the first term in your series if these match up. Are you clear? Okay, so this would be the geometric series. Your A is 2/3. Your R is 2/3. That would be your sum. It'd be 2/3 over 1 minus 2/3. Show of hands if you feel okay with that one. Now, here's my next question. Should I have done that?
No.
Let's go to the next one. Minus. Tell me something about this series. What's my R again? So you could strip this off and do n equals 1 to infinity of 5/3 times 5/3 to the n minus 1. You could do that. But notice, when you strip off one of those fractions, does your R change at all?
No.
Just the power change. So your R is not going to ever change here. Tell me something about the R. Is it more than 1 or less than 1?
Greater than 1.
Bam! You know something about geometric series when the R is greater than 1. Tell me about that. So we got a sum minus something that is divergent. If you have a sum minus something that is divergent, this is a real number, right? That's something. This is, I don't know what that is. It's infinity, actually, because you have 5/3. That's getting bigger and bigger and bigger because it's more than 1. This is going to be infinity. So you have something minus infinity. Can you tell me what the sum of my series is if you have something minus infinity? No. Listen, if you break up a series, each one of these parts would have to be convergent for the whole series to be convergent. If one little piece is divergent, then the whole series is divergent. Not sure if you just heard me, feel okay with that. So let's imagine that this was 1/3. And this was 1/3. Would this be convergent? In this case, you would do 1/3 over 1 minus 1/3. You'd figure out this sum, you'd figure out this sum, and you would subtract them, and that would give you the sum of your series. Show of hands if you feel okay with this idea. Now, do you want to see a little shortcut when you deal with this stuff like this, where the powers don't match exactly? You want to see a shortcut for that?
Yes.
Okay, sometimes I'll teach this, sometimes I don't. I think you guys can handle it. So I'll give you the shortcut. Okay, so here's our formula. If we have this, or we have this, if we have this or this, well, then we know that the sum would be given by those two expressions. It doesn't change. Even though my index is different, even though my power is different. Here's the whole reason why this doesn't change. The whole reason why this doesn't change is because I don't care what this is, if my first power is 0, that means I'm going to get A as my first term. Does that make sense to you? It's always going to be the first term. If my first power is, oh, hey, 1 minus 1, that's 0. My first power is 0, A is going to be my first term. So basically, listen carefully here, because this is where I'm going to get my shortcut from. Basically, A stands for the first term in your series. Look at this. If I plug in 0 for my n, what's r to the n? 1. A would be my first term in my series. You can make shortcuts with this. Let me give you an example. I'll give you one like this one. Tell you what, instead of actually matching this up, here's what you can do with it. If you understand that A is always the first term in my series, then here's what I can do. I can plug in 1 here. When I plug in 1, what's 2/3 to the first power?
2/3.
I can take my first term in my series. Notice how 2/3 would be my first term in my series. If I were actually to do this, right? I'd plug in 1, then I'd plug in 2, then I'd plug in 3. 2/3 would be the very first one, wouldn't it? 2/3 over 1 minus 2/3. You just take the first term. You actually do the work. Plug in whatever this index is. Take the first term, 1 minus whatever your r is. Because we know our r is not going to change by stripping off these fractions, your r, don't worry about your r. It's never going to change. As soon as you get in this format, your r would never change. You're just worried about your first term. Since I've shown you here that A is always your first term, we can kind of cheat at it a bit. Did that make sense to you?
Yeah.
I'll give you one more example so that way you can really see it. Okay, this one's I think I just made this one up a little while ago, and I want to show you. So example. You guys ready for it? I'm going to do much with this example, so stick with me. Of course, before we do anything with this, you need to recognize that this is a geometric series. And the way that I see that, I go, well, wait a minute. I've got a constant, easy constant, to a power, and I have a constant to a power that's based in n. That right there says to me geometric. Does that make sense to you? It's a constant to n and a constant to an n. That means that if it's not the same n, I can strip some off or put some in, whatever. But ultimately, I'm going to be able to get a fraction to an n power. That's what says geometric about this to me. Now, we can work with this. That's not too bad. If I have n equals 2 to infinity of e to the n over 3 to the n plus 1, that's the same thing as 3 times 3 to the n. Show of hands if that makes sense to you. Now, I'm going to break this up a little bit. I'm going to get n equals 2 to the infinity of 1/3. Notice my 1/3, and then I'll have e over 3 to the n. I need a big show of hands if you understand the algebra of this thing. In the middle, we okay? Okay. Now here's my point. This is a geometric series, correct? Correct?
Yes.
Here's my question. Do you know how much the A is?
Yes.
If you tell me 1/3, you're wrong. Is the A 1/3?
No.
No. The A is not 1/3. Here's why the A is not 1/3. Does your index match your power? Which means, when I plug my index in, is my first power 0?
No.
That's how geometric series works, okay? If the first power is not 0, that means this is not your first term. That's the problem. Does that make sense to you? That's the problem. This has to, listen, I'll make it very cut and dry. For these formulas to work, this has to be your first term. If it ain't your first term, that formula don't work. Does that make sense? So, the reason why I rarely teach, I think you guys are smart enough, you'll pick it up, okay? The reason why I rarely teach this is because people, when they get this, they forget they have to match, and they do this. They go, oh, my A is 1/3, I can do 1 minus e over 3. Big mistake. Big mistake. There's now 2 options that you have for going around this. The first option is the old way, and it's not that hard. All you got to do is just match up this with this. So, if this is 2, if this is 0, I need n. If this is 1, I need n minus 1. If this is 2, I need n minus 2. That's it. So, option number 1. You could do it the old way and just do, okay, if this is starting at 2, I can do 1/3. I can split off an e over 3 squared. So basically e squared over 3 squared. I can split that off. Split off an e over 3 squared. And then I'll have an e over 3 to the n minus 2. I'm curious, do you see that this is the same thing as this? Do you see that?
Yes.
Do you see that this whole thing's a constant? That would be n equals 2, oops, that's not right. 2 to infinity. This would be e squared over 27. Verify that for me, please. This would be e squared over 27. Now let me ask you a few questions about this. If you plug in 2, is your first power 0?
Yes.
That means this is geometric and it fits my form. All you have to have is the first power being 0, because then what that means is this is your very first term. If this is your very first term, then I get to do my sum formula as e squared over 27, 1 minus e to the third. Notice how no matter what, our e over 3, sorry, not e to the third, e over 3. Our e over 3 is not changing, even though we're stripping out parts of that fraction. It's not changing. That's now my sum. Yeah, of course you would simplify that, right? But I'm just trying to give you an example here. Did that one make sense to you? Now here's a shortcut for doing this. Here's a shortcut. Check it out. From right here, so or, not both, or. If you're good at this, if you're really good at this, here's what you do. You understand that what A is really the first term in your series. You go, okay, well, duh. If this gives me a 2 minus 2 is 0, this whole thing is 1, that's the first term I start with. Well, you can do that from here. Just plug in 2. If you plug in 2, you're going to get, hey, look at that, e squared over 9, huh? E squared, do you see the e squared over 9? I was looking at the, do you see the e squared over 9? If you got e squared over 9, e squared over 9 times 1/3 is e squared over 27. Hey, that's the first term in my series. Is the r going to change? No. 1 minus e over 3. Do we get the same thing? It's just a little bit less steps. The only problem, and I'm praying that you see this, students have an issue when they don't understand what's going on. They don't understand this is the first term, that's what A really stands for, that's the first term of your series, and what they end up doing is they go, oh, my A is 1/3. Mr. Leonard says, I don't care if those match up. No, Mr. Leonard says, care. You gotta care. You have to. This has to be an n minus 2 for you to legitimately use that formula. It's got to match up your power with your index. It must. If it doesn't, then you have to think harder. You think, okay, well, I know that A is really just my first term of my series, so if I plug in my first index of 2, the first term of my series is not 1/3, it's e squared over 27. That's the idea. So does that make sense to you? Cool, excellent job. Also, one last bit of advice. Do not forget about the divergence test. Don't forget about that. You can check series very quickly by divergence test. And that's what you should do every time you get a series. Take a limit of it. Take a limit. If that limit does not equal 0, what do you know about your series? Divergence. That'll save you a lot of time on this homework, okay? Now, the next thing we're going to talk about. Questions?
So pretty much what you're doing is whatever n equals, you just take it to that power.
If this is 0, minus 0. If this is 1, minus 1. If this is 2, minus 2. If this is 3, minus 3. If this is 4, minus 4. You need the first power to be 0. If that's true, then A stands for your first term. If that's not true, you figure out your first term. Make sense? Yeah. Now.